So question 2, we've got a graph here and it's obviously disconnected, and part A says what's the smallest number of edges to be added to ensure that the graph is connected. So let's have a look. I've got myself a copy of the graph here so that we can look at it. So to be connected, we obviously need to add in 2 edges. This is one way of doing it, but we've just got to make sure that there's a path from every vertex to every other vertex. That's the definition of a connected graph. To be complete, so we've got 5 vertices and every vertex has got to be joined to every other. So for example, here at workshop D, then this one vertex is complete because the workshop D is connected to 1, 2, 3, 4, the other 4 vertices. Now, we've got to do that for 5 vertices, so that's 5 times 4 is 20, but then we would have doubled up on the number of edges, so then we halve it, and that gives us 10, but we've already got 2 edges in the network, so then we've got to take off 2 and we're left with adding 8 edges to make it complete. And then the last one, planar with 4 regions. So planar just basically means it can be drawn in the plane without any edges crossing, and we've got to make sure there are 4 regions on it. So that means we've got 1 region at the moment. We're going to need to add 3 loops or 3 edges so that we get the 4 required there. So here's my diagram, a little bit small, but you can see we've got the smallest circle on the inside, then on the in-between and the outside, and then the outside region. So 3 edges for that one. Over the page, it carries on 3 different plans for completing the network as shown by where we've added 4 walkways. And then we've got to answer some questions on these graphs. So state which, if any, of these plans has a graph that is bipartite. So in a bipartite graph, can never have any triangles. That's a very quick way of identifying a bipartite graph. If you spot a triangle like in this one here for plan P, then you know it's not going to happen. So this one can't. And plan R, here's a triangle, so this one can't. But plan Q looks like it could. I'll just get a highlighter here and let's just check out. We'll do the alternate coloring. So C is one color, B stays plain, D goes colored, A stays plain, E stays colored, we're back to B. And so there it is. It is bipartite. C, D, and E form one set of vertices and A and B the other. So that's all okay. And then the last... the second one, Eulerian here. So any of these graphs Eulerian. So basically we're checking out to be Eulerian. All the vertices have got to be an even degree. And here's one. So on plan P, that's not going to work. On plan Q, B is 3, order 3, so that's not going to work. And on plan R, D is order 3, so it's not going to work. So we answer none. And then on the last question, a Hamilton cycle, that means we've got to start and finish at the same vertex and visit all the others without going along any edges more than once. So the only way to do this really is an exhaustive search. So it looks like we can do it at P, simply hoon around the outside. A, B, C, D, E, and back to A, so that gets the tick. Plan B, if we start at A, say, and go, well, where will we go? Let's go up to C, across to B. Then when we're at B, we've got to go to D, but then the only way is to get back to E. So if we went from C, when we went to B instead of went to E, we'll end up back at A. So either way, it looks like plan Q is not working. Plan R, let's start at A and go up to C and then across to B and down to D and across to E and back to A. So that one works as well. So P and R work nicely.